I'm Michaela. I'm a self-employed front-end developer and web and UX designer from Berlin. And today I want to tell you a little story about how I learned lots about the Web Bluetooth API and the Web Audio API by kind of hacking my Vibrator. So let's get started. The situation was the following. So there was me, and there was this super cool new Bluetooth-enabled vibrator, and there was the instruction telling me that all I need to add now was a partner with a smartphone. And that was kind of unsatisfying. So not that I did not want to add a partner in general, but I thought I should be able to use my Bluetooth technology all by myself. And I mean, I could just remove the partner and leave the smartphone, but this wouldn't be that fun and surprising. So I thought, why not use a video? I mean, a fitting video for that purpose can be found in the internet. It couldn't be that hard. So why not use a video, which obviously comes with sound, so why not use the sound or specific sounds from that video to trigger the app, or rather the Bluetooth device directly. And luckily, I'm a web developer, which means I read Twitter a lot. And I remembered a post about Chrome adding support for a Web Bluetooth API. And this API sounded like the perfect fit to my use case and my skills. So that's what I did. I used a browser with support for the Web Bluetooth API and the Bluetooth-enabled Vibrator, which had the required Bluetooth 4.0 support to connect the Vibrator to the browser. In detail, I had to make 3 steps to achieve my goal. The first is request my goal. Yeah. The first was request the Bluetooth connection from the browser to my device and then connect them. Then I would have to read the audio data from the video to recognize the vowels, or in my case especially the R's. And afterwards, write the data to the Bluetooth device with the Web Bluetooth API. And therefore, I also had to figure out what commands to write exactly. Okay, now to the first step. How can we connect a Bluetooth device to the browser anyway? This is the part where the Web Bluetooth API comes into play. The API provides the ability to connect and interact with Bluetooth Low Energy devices. And Bluetooth Low Energy, or Bluetooth LE, is part of the Bluetooth 4.0 specification since December 2009. Like with the original Bluetooth, devices within around a 10-meter range can connect using short-range radio waves like our Wi-Fi does. And on the right, Bluetooth Smart is generally speaking another name to Bluetooth for Bluetooth Low Energy. So devices that support Bluetooth 4.0 or higher can be used with the Web Bluetooth API. This includes, for example, iOS devices since iOS 5, and all Android devices since Jelly Bean, Macs since Snow Leopard or higher, and Windows computers with Windows 8 or higher. Okay, now I know it's a bit off topic, but I could not resist mentioning this, especially speaking here in Oslo. The name Bluetooth is a tribute to Harald Blatant Gormson, who lived around 958 to 986, and he was king of Norway and Denmark. And he was also known for his good communication skills, which helped him unite Denmark again. That's what I read, anyway. Since Bluetooth was mainly developed by employees from Ericsson, a Swedish company, and Nokia, a Finnish company, the developers chose the name Bluetooth as a working title. And as you all know for sure really well, a working title often sticks, because when launching a product, everything else seems more important. In my opinion, I find this is a good choice. They also decided that the logo should be the 2 initials of Harald Blatant as Old Nordic runes, the Haglas and the Bergkanan. Okay, enough trivia for now. Let's see how connecting with a Bluetooth device works. So we have a peripheral device, which in most cases is a small, low-power device, in my cases, my vibrator. And we have the more powerful central device, which in my case was my MacBook with Chrome. And both will eventually communicate with one another using a technique that is used by our Wi-Fi, like I said, and that is called frequency hopping spread spectrum, which means that the frequency channel is not exactly 2.4 gigahertz, but it hops rapidly between many channels around 2.4 gigahertz to reduce interference. The first step would be of the connection process would be made by the peripheral device. It sends its advertising packet within a specific advertising interval again and again until a listening device is interested. And if the listening device, the central device, is interested in sending or getting data from the device, it can send a scan response request, waiting for the scan response answer, the data from the peripheral device. What is good to know maybe is that a peripheral device can only be connected to one central device, while a central device, like my MacBook, can be connected to multiple peripheral devices. An exception there would be, and maybe you have heard of it, devices like Apple's iBeacon. They are also peripheral devices, but they do not want to connect to any central devices at all, but they just want to send out advertised data, which is known as broadcasting. Okay, but this is not the thing we want to build. We want to establish a real connection and then communicate with the peripheral device and send data to it. To do this, we will have to use GATT, which means generic attribute profile. And this profile defines the way two Bluetooth devices transfer data back and forth using so-called characteristics and services. In this case, our peripheral device is the GATT server, and the central device is the GATT client. And the client can send GATT commands and requests and accept the server's responses, and the GATT server receives commands and requests made by the client and returns responses. Okay, now how does the communication work exactly? On the lowest level, we would have characteristics which encapsulate a single data point. A characteristic can whether be read-only, in this case we call it the RX channel, or we can write to the characteristic sending data, which we will call the TX channel. And a service is used to contain a collection of related characteristics, which makes it possible to break the data up into logic entities. And around this, the profile is a predefined collection of services that does actually not exist on the Bluetooth peripheral device, but is compiled by the Bluetooth special interest group or peripheral device designers. For example, there's a heart rate profile that combines a heart rate service and a device information service. And coupling characteristics and putting them into a hierarchical order with services and all that stuff seems kind of complicated, but it is necessary to reduce the transferred data and not have so much impact on the battery. Okay, let's take a look at the JavaScript to do this. I will show you some code snippets so that you'll get the feeling of how it could work. So first, we need to request the peripheral device, which for security reasons can only be triggered by a user action. And then the navigator Bluetooth request device function takes an object as argument that defines filters. And they are used to return only devices that match some advertised Bluetooth GET services or the device's name, for example. You could request scanning for all Bluetooth devices in the area, but this is really not recommended because it also has impacts on the battery. So in my case, I'm filtering to find the service of my special device, which I call Lush service. And because there was no real documentation for the vibrator, at least not for this case, I had to look up the service's name in another way. And to finally get the name of the GET service, I used an Android app called NRF Connect, which shows you all the Bluetooth devices in your range and some information about them. NRF Connect then also showed me that the devices service is a Nordic UART service, which is a GET service to get and write data from a peripheral. And there's the long string I used then in the code. Okay, now the request device promise returns the Bluetooth device object, which we can use then to connect to the device's GET server. And the GET connect promise then returns the GET server, which holds the service and both characteristic definitions that we can use to send or get data from the vibrator. So this is how it would look. Yeah, let's play the video. So this is the vibrator, or the peripheral device. And as you can see, it was blinking, which means it was on but not connected. And next, then I click to the button, connect to the device. And there we can see, sorry, it's really shaky. There we can see that I found the device and the server. Yeah, one more thing, the vibrator does not really come with these googly eyes, but I added them to make them more conference-friendly, which is also why I have hundreds of googly eyes now, because you cannot just buy two. So if someone wants them, just grab me after the last talk and I can give you some. Okay. Before we now write data to the Bluetooth API, with the Bluetooth API to the device, let's take a look at the second step and analyze the audio data with the Web Audio API. So this is actually not a new API. I guess you have all heard about the Web Audio API before. It is really widely supported. I think only Opera Mini does not support it, and we can use it for many, many years now. But even though I studied musicology and wrote my master's thesis about audio analyzation, I never really used it for analyzing audio files till now. So it was kind of new to me too. The Web Audio API can be used to control audio in the web, and to do this we have to create a so-called audio context in which we can create multiple audio nodes to control or analyze or edit the sound files. In detail, first, we would have to create an audio context to manage and play all sounds, and then we can create these various audio nodes and link them into chains or webs by using their inputs and outputs. We would usually start with a source node that itself has no source input, but can have one or multiple outputs. And it can be used to generate the sound at the beginning. For example, we could use an HTML audio element or the video element, or manually create sounds with an oscillator node, for example. We end typically with a destination node that, on the opposite, has only an input but no output. Instead, all inputs are directly played on your speakers. And between those two nodes, we can modify and analyze the sound with processing nodes, which have both input and output. For example, we could add sound effects like a reverb, or in our case, we get the frequency data. And all this together is called an audio routing graph. Okay, now we know how analyzing audio in general would work in the browser, but this is what I asked me then now. What exactly are vowels, or what is sound? So sound is a vibration. We talked about frequencies, and now we're talking about other frequencies now. Sound is a vibration, typically a wave of pressure through gas or liquid or solid material. And humans can hear sound of certain frequencies between 20 hertz and 20,000 hertz. So sound waves below 20 hertz are known as subsonic infrasound, and sounds above 20,000 hertz are known as ultrasonic sounds, and we don't hear both. What is important for us to know is that a complicated sound wave can be represented as a mixture of different sinus waves with different frequencies and thus different pitch levels. Here you can see on the left in red For example, a complicated sound wave, which could be a tone from an instrument or a spoken or sung voice. And since we can deconstruct the complicated sound waves into single sinus waves, we can get all sinus waves and therefore all pitches at a single point of time. And this is what you see then on the right in blue. It's a frequency spectrum representing all frequencies hearable at a single point in time. The method to get the frequency spectrum is called Fourier Transformation. And with it, we can then decompose a continuous aperiodic signal, like our sound, into a spectrum showing us all the frequencies and their volume at a single point in time. Yeah, and we can use this to recognize vowels. We have to look at the frequency spectrum and check which frequencies are louder than others. And these are called formants. They are usually a lot of louder parts or formants in a frequency spectrum made by an instrument or a voice. And for a spoken voice, the first two formants, F1 and F2, are responsible to form a vowel, and only the third and fourth formants are responsible for our voice's tone, the characteristic of our voice. So we are interested in the R's, and that's why we are looking for formants around 800 hertz and around 1600 hertz. Okay, now how do we find the vowels in the sound of a video element? First, we would have to create the audio context and the audio nodes. And to get the audio from the video, we can use the media stream audio source node. And to get the frequency spectrum, we can use the analyzer node. The next step then would be connecting these nodes. And we start with the media stream audio source, connect it to the analyzer node, and then to the destination, which is actually just the audio rendering device, such as my speakers. In code, this could look like this. We create the audio context, the stream element, the media stream source node, and the analyzer node, before then connecting them to build a chain. The analyzer node does the Fourier transformation for us, or to be exactly, it uses an algorithm called fast Fourier transformation. And this gives us the frequency data with one single function. Except from giving us the data of the frequencies and stuff, the analyzer node does nothing to the sound. It just stays unchanged from input to output. So in detail, we would have to set an FFT size, fast Fourier transformation, and this size represents a little time window that is used for performing the fast Fourier transformation. And a higher value of this window would result in more details in the frequency domain and fewer details in the time domain. The frequency bin count, is half of the FFT size, and it equates the number of single data values we get from the Fourier transformation. So then we can create an array of 8-bit unsigned integers with the length of the number of the data values, which was the frequency bin count. And then we call the data collection method getByteFrequencyData with an array as its argument to retrieve and copy the data directly into our array. And to do this process again and again, and also because I was using Canvas anyway to render frequency spectrum, I used the request animation frame function. And within it, I constantly get the frequency data and use it to get first the formants, and then the vowels. So this is how the frequency data looks like. We get 1024 data values representing the volume of a frequency in a normalized array of values between 0 and 255. And to get the loudness in percent, we can divide the value by 256. And to get the frequency of each value, which we also need, we can multiply the value with the sample rate and then divide it with the FFT size. So the sample rate is the number of audio samples per second of our video sound. In this case, it was for 44,100. Okay, with this data, then we can get the formants by detecting the highest volume within the specific range of the spectrum. And first, we get the frequency and the volume values, and then, while looping through the data, we check for frequencies lower than 1000 Hertz to get the first formant, and to get the second formant, F2, we check for frequencies lower than 5000 Hertz. And then I save the highest value, return both formants and their frequency and their volume data. So to get the formants that only match the R's, we check, we use the function formants to R, and we check if the formants are within the correct frequency range and if they are loud. And if so, we just return the vowel as a string. Now, within the render function, I can now check if a vowel was detected, and this is the point where that we would then later have to trigger the vibrator and by writing to the characteristic. But first, let's take a look at the video and see how it works. This is obviously not the video I was using while making the prototype. But I figured, yeah, adult videos would be also very inappropriate here and probably also not or against the code of conduct. So I had to find a video that uses similar sounds like the one I had in my original video. And first, I used the music video, but that didn't work nicely because the sung voice has different vowel formats than a spoken voice. So then I thought of tennis. But that was kind of boring. But luckily, I had a better idea. So Buffy is not only the best series in the world, but it has various fighting scenes that have similar sounds, like my video. And it worked more or less with my prototype. And this scene of episode 11 of season 1. And for those of you who are curious, this episode is called Out of Mind, Out of Sight, and it was written by Joss Whedon himself and aired on May 19th in 1997. Yeah, now I'm confused. Let's go back to the topic. To make the detected vowels visible in this demo, I used the body's background color and made it pink when it happened. And for debugging reasons, like I said, I also added the canvas rendering the frequency spectrum. So now let's go and see if the sound works.
I see right through you. Oh my God, get me out of here, please. Hold still. Oh my God. You know, I really felt sorry for you. You suffered. There's one thing I really didn't factor into all this. You're a thundering loony. Buffy, are you okay? Oh my God! Oh my God! Buffy! Buffy! Oh my God! Hey, moron! I'm invisible. I'm gonna fight someone you can't see. Oh my God! Cordelia, shut up.
It's a good episode. Yeah. So second step done. And now we know when a vowel is happening, and we just have to find out how to send commands to the device to start and stop vibrating whenever a vowel was recognized. And usually you can look up these commands in a documentation or the Bluetooth GET characteristic specifications directly, but both did not work in my case. So I used the official app that comes with the vibrator and logged the Bluetooth traffic. And what I got was this hexadecimal ASCII value that I then translated very professionally with a random online converter. And I got, ta-da, a string that really looked like I was on the correct path here. So let's get back to the code. You remember we connected to the GET server and its service, right? Now to write data to the device, we have to use the TX characteristic of this GET service. And after connecting to the GET server, we request its primary service. And from the return service, we get the TX characteristic with the get characteristic method. Again, we have to use a UUID of this characteristic. And again, I use the nrfconnect app to get this string. To use the characteristic within the render function, later when we actually found vowels, I saved it in a variable. And when a vowel was found, I encoded the string command to an ASCII value with the new text encoder function and send it to the device with the write value method. For your info, the new text encoder and decoder function are currently not working in Edge and Internet Explorer, but since I was using Chrome, that was okay for the minute. Yeah, and I hope you're ready to watch Buffy once more, because now there's the final demo. You get the characteristics. It was actually hard to make it stand still there.
I see right through you. Oh my God, give me a hand, please. Hold still. Oh my God. You know, I really felt sorry for you. You've suffered. There's one thing I really didn't factor into all this. You're a thundering loony.
Use the max value too.
Are you okay? Oh my God! Oh my God! Buffy! Oh my God! Hey, moron! I'm invisible. I'm gonna fight someone you can't see. Oh my God! Cordelia, shut up.
Yeah, and that's basically all from me. I mean, I could have done way more, and I'm continuing to improve the vowel recognition, and also I would like to use the loudness of the vowel to trigger different vibration values, which would be really cool. But for now, that's all I got. If I had a free wish, I would like you to remember two things from this talk. And the first thing would be creative. With JavaScript and the web APIs, we can do so much, especially when combining them. And the second, if you like experimenting with new APIs, give feedback to the persons writing them. Yeah. And if you're interested in more information, I have a link, a slide with links afterwards, and I will upload the slides after the talk or tomorrow. Thank you.
All right. Thank you so much. All right. That actually seemed pretty difficult to do. Like, what is your feedback for the API developers? Which ones were the most difficult to figure out? And
for me, it was more difficult handling the frequency data than the Bluetooth API. I find it really straightforward, like connect. Only promises.
Yeah.
Yeah.
Okay. Well, there's one question, which is, what is the best Buffy character and why?
Of course, it's Buffy. Yeah, of course, it's Buffy. And why? Because she's a heroine and she saved the world a lot.
Is there anything else you want to say, I guess, about
No. I'm done.
All right. Thank you so much.
Thank you.